this lecture, we shall derive the different alternative forms of vector theorems, namely Stokes theorem and Divergence theorem. The Stokes theorem is curl of any vector field in the surface integration, where C is the contour which bounds the surface S, and A is a vector point function which is finite everywhere on S and on C, everywhere in S and on C. And since we need to calculate the curl of A, so A must possess first order partial derivative. So A is finite. Requirement is A is, firstly, S is the surface bounded by contour C, at first point. Secondly, A is finite everywhere in S and on C. That is, A is defined everywhere on the surface, everywhere on the surface and on the contour. Thirdly, del A x, del y, etc. The partial derivatives. The partial derivatives of A components of A exist. If these conditions are satisfied, then the Stokes theorem is valid for any vector field of satisfying this condition. We first want to, here we shall derive the different alternative forms of Stokes theorem. As for example, let us consider that a case where the vector field A is written as some scalar point function phi of r times a vector C, where C is any arbitrary constant vector. C is an arbitrary constant vector. Then what happens to the form of this? Then A dot dr can be written as phi times C dot dr, which we write C dot phi dr. And coming to the left hand side, it is curl of A dot ds, curl of phi times C dot ds. So this is phi times curl of C plus grad phi cos C dot ds. Since C is a constant vector, curl of C is 0, and we can write it as, this is a scalar triple product involving three vectors, grad phi, C and ds. So we can write it as C dot ds times grad phi. In coming from this stage to this stage, we have made two interchanges, C and phi. One is C and grad phi, and then grad phi and ds. So this is two interchange, there is no change in sign, and we can put dot and cross anywhere for scalar tuple product. So this is the result. So if we apply this using this condition, and the final result of this, we have surface integration C dot ds grad phi is equal to contour integration C dot phi dr. Or since C is constant, it can be taken out and we write it as surface integration ds cross grad phi minus contour integration phi dr is equal to 0. And this relation is valid for every C, because C is arbitrary. As C is arbitrary, the quantity within the square bracket must be 0. And if we transfer the side, we get the alternative form of Stokes theorem phi dot dr, where we have applied the Stokes theorem on a scalar point function. So the alternative form is this is one thing. Another form is that when one writes A as the curl of two vectors, of which obviously one is arbitrary constant vector C. So we write it as C cross B, where C is again a arbitrary constant vector and B is another vector field which possesses properties similar to that of A. So coming to the right hand side, A dot dr now becomes C cross B dot dr, which can be written as C dot B cross dr. Now the quantity on the left hand side, curl of A dot ds, it is curl of C cross B dot ds. This involves a mathematical vector identity which involves 4 terms. But here we shall opt some other technique, which we consider that nabla, since C is constant vector, nabla does not operate on C, but nabla operates only on B. And nabla operating on C gives you either this or curl C, both of them 0, as C is a constant vector. So we are not considering the operation of nabla on C, and we'll write this as divergence B times C here we have used one thing, is that we have used the back-cap rule, that is the rule A cross B cross C is equal to B dot SC minus C dot AB, which is known as back-cap rule. Here we have used back-cap rule and we have kept in mind that nabla can operate only on B, not on C. That's why it is written as C dot nabla and B is written on the right. So this part, the first term can be written as C dot This is the first term, and the second term is written as minus C dot grad operating on B dot ds. Taking C dot common, we have now we can use the reverse back-cab rule. If we rewrite reverse back-cab rule, what will happen? It is C dot is there, then the common term is B, so first term is B cross, this is ds cross grad. If we use the reverse back-cab rule, the result is this, but this is not a valid result because nabla has to operate on B. So what should we do? We interchange this and this. So we write as minus C dot ds cross nabla operating on B. So if we apply this result on we get on the left hand side minus C dot surface integration ds cross B is equal to C dot contour integration B dot D, B cross dr. Since C is arbitrary, we can write the third alternative form as surface integration ds cross nabla operating on B in curl mode is equal to contour integration dr cross B. This is the second alternative form. In writing the final form, this minus sign has been adjusted by interchanging the order of curl operation. So these are the three alternative forms of Stokes theorem. Now we come to the divergence theorem. The divergence theorem relates a closed surface integration of a vector field with the volume integration. So divergence theorem in its normal form, it is divergence of A integrated over V is equal to closed surface integration A dot ds, where S is the closed surface which bounds the volume V. First thing is that we write A as phi times C as we did in the earlier case, and consider C to be a constant arbitrary constant vector. So A dot ds becomes C dot phi ds, and divergence of A dv is equal to divergence of phi times C dv, and this part is phi times divergence C and grad phi dot C dv. Since C is a constant vector, this is 0, and we have grad phi dot C dv, which can be written as C dot grad phi dv. And the theorem becomes closed surface integration phi dot ds. This form of divergence theorem can directly be applied on a scalar point function. Another form is, as usual, A is written as C cross B, again C being a arbitrary constant vector, and A dot ds, in which case becomes C cross B dot ds, which can be written as C dot B cross ds. This is one part, and the other part is divergence of A dv. This is divergence of C cross B dv. Here divergence, this operates only on B, not on C. Now remembering this, we can write it as minus C dot curl of B dv. And when we apply this, this one and this one, we get on left hand side we get minus curl of B dv over integrated over V is equal to B cross ds, so that the result becomes curl B dv is equal to surface integration ds cross B. One thing, notice that these three forms of divergence theorem enables us to define divergence, gradient and curl in terms of integrals. If we apply this over a small volume B going to delta V, so that is going to delta S, and we consider that volume is so small that gradient of A remains almost constant on this volume, in which case we can write divergence of A is equal to limit delta V tends to 0, consequently delta S tends to 0 on delta S A dot ds by delta V. This is the definition of divergence. Then gradient, limit delta V tends to 0, consequently delta S tends to 0, and on the this gives you the definition of divergence. And finally coming to curl, from the third form we get curl, definition of curl as the limit delta V tends to 0, delta S tends to 0. This is equal to surface integration over delta S ds cross V upon delta V. These are the integral definitions of divergence, gradient and curl. There are two other forms of vector theorem, of divergence theorem, which is found to be very helpful in different branches of physics. They are called the Green's identities. Let us write vector A of this divergence theorem as f times grad g, where f and g are scalar point functions having well-behaved forms, so that divergence of A is equal to divergence of f times grad z, which can be written as f times, and if we apply the then the theorem becomes divergence of f times grads over v is equal to surface integration f grad z dot ds. This is known as Green's first identity. If we write once A as this, we get this, and if we write A as g times f, we get integration over v g times dv. On the other hand, we have g grad f dot ds. If we subtract this from this, we get volume integration f grad square g nabla square g times g nabla square f integrated over volume v is equal to surface integration f. This is known as Green's second identity. They are very helpful in different branches of physics. One thing I forgot to mention, that the definition of divergence, curl, and gradient that we have given in terms of vector theorems, they are the general theorems valid in Cartesian as well as other different coordinate systems. Initially, we started the definition of divergence and curl in terms of Cartesian components and extended for different coordinate systems. If we use this definition of divergence, that is, if we write divergence of A as limit delta v tends to 0, delta s tends to 0, then surface integration A dot ds over delta of a surface divided by delta v. Such definitions are valid in all coordinate systems, Cartesian as well as non-Cartesian. So this is one beauty of it. This relation is valid because on the right hand side we have written the operation in terms of in vector form, and vector relation are valid in all coordinate system. But if we write the relation in 3 components form, then the component forms are valid only in specific coordinate system. So this is the first lecture on mathematical preliminaries that we shall require for the development of the course electricity magnetism. These alternative forms of vector theorem will be needed, and in the next class I shall consider the decomposition and uniqueness theorem of vector fields.